as we mentioned earlier, let us discuss the principle behind many of the random algorithms. There is a fundamental concept in statistical learning, or we can call that extract information from data for future prediction. It is called a bias versus variance. So what is bias and what is variance? Let's start from the learning framework. I have to remind you at the beginning that this part is totally optional. Skipping this part will not affect your ability to implement any of the algorithms we have introduced or we will introduce in this semester. So that is for students with a more theoretical interest in the design principle. But look, understand the fundamental learning framework will, however, help you when facing your own data analytics problems to choose or to modify, adopt your specific learning algorithm. Let us begin. So in a sense that all learning algorithms are stochastic. If we overstretch the notion of random algorithms or stochastic algorithms a little bit, because if we think the entire process of learning this, we get the data. In this figure, I put the data here, the observable part x and the target value y. From the data, the learning algorithm refers to the observed data, the proven, the provided training data set, and according to some criteria, a loss, this training algorithm find, and it is also referred to another space. And that space, we call it a hypothesis space, which can be understood as a family of models. So the learning algorithm have in one hand the data and in the other hand the hypothesis space or the models, and in its mind it is to minimize the loss. So with respect to the minimal loss criteria, it chooses some optimal, well, according to its view, the optimal hypothesis or the value or the model to return to you. And this H star, if we correspond this notion to what we have already done, is the data model that has been where the fit function has been called. If you remember, if we follow the interface of scikit-learn, many of the data model has a fit function. After fit, the model's parameters has been determined with respect to the training data, and the fit function, of course, accept x and y training samples. But in this entire procedure, although at this view we cannot say if the learning algorithm is deterministic, the procedure has been determined previously without the random sampling steps we have just introduced in the boosting or bagging algorithms. So in this procedure, one may not see where why we can call any algorithm stochastic. But look, the observed data, if we consider it carefully, is from some unknown data population. So it is entirely possible if we do the observation again, we will have another training set. So let's call the previous one training set 1 and this one training set 2. For the second training set, even we use a deterministic learning algorithm as with the exactly same model family or the hypothesis space and exactly the same criteria for optimization, we will arrive probably a different so far we can see optimal hypothesis or model, and so on and so forth. So actually there are infinite possibilities that we can get the training data and arrive the models, arrive different predictive models. The concept of bias and variance is with respect to the distribution of this differently achieved learned data models. Note, when we consider some stochastic events, normally that is a personal suggestion. For me, when I try to understand notions that is stochastic, I generally want to find where is the source of the randomness. That is, if I repeat the entire procedure from scratch, where and arrive a different result. Of course, otherwise it won't be a stochastic process. And I would like to track the reason why I will have the difference comes from. And in the learning procedure, the difference probably comes from that you may have observed a different set of training data. Okay. And here we introduce the notion of bias and variance. With respect to all those learned data models resulted from differently observed training samples. Say if we have this infinite number of learned models, that is of course assumes that we have infinite number of training samples that we have we are ready to define the notion of bias. Consider that if we can get infinite number of training examples, that is, we can get infinite sets of training examples, and from the infinite sets, each of those infinitely many sets, we learn a model H. So from H1 to H infinite. For all those models, let's forget for a minute that where can we procure infinite number of training sets. So say assumably, let's no, not very assumably, let us just assume that we have such infinite number of learned examples. If we average over all those all those learned models and have some average H, say this H bar. Let's say for regression, let's consider a regression problem for simplicity. The prediction by H bar will be the average prediction of all those H star 1 to H star infinity. That is, for any given x, H bar will output average y, and that y would be the mean of the same x to all the infinitely many learned h, and let those h to produce a corresponding prediction y, and we take the average of all those y's to have such a mean, and that would be the output of our h bar. Okay, so consider if we consider a loss in L2 that is considered the squared, the mean squared error, h bar would be the optimal choice we would have, given that if we were having infinite training samples to spend to train the models. Okay. In this slide, we represent this concept a little bit in a more formal format. So let L represent the loss, and H bar represent the average model. And H bar, if we write it explicitly, is the expectation. We can consider it as mean value for simplicity, and less rigorously. The expectation over what? Over this D, this capital D, and the D represent data. The data consists of training observations and training targets. That is the training data set. That is taking expectation over all possible training sets. And this capital A represents the learning algorithm. Use a particular learning algorithm, provide the algorithm the data set, and the algorithm will produce some H. If we use this produced H, the bracket should be a little bit further to include this X or whatever. We average over all the data sets and have an average H, and use this H bar to predict X, and compare this prediction with Y, and this loss in the mean squared error sense would be the optimal performance of a particular learning model. By a particular learning model, I mean if we fix the learning algorithm and fix all the possible hypotheses, the model family, the model family from which we can train a model. If we fix the algorithm and the hypothesis set, that H bar would be our optimal choice, because the information that we have summarized into H bar for prediction is from assumed infinite number of training samples. Of course, that notion is just hypothetical, because in practice, no one is going to have an infinite number of training samples. The entire business of learning from data is that, given limited observation of the data population, and have general assumption that hopefully hold true, that the test data will come from the same distribution as the training data. We learn some algorithm to do the predictions on the test data, hopefully. Okay, so this is optimal expected error between the H bar and the target value Y would be the bias of a model family. Look, bias is with respect to the model family. Here we save the learning algorithm from this representation, because learning algorithm is in many cases is less flexible. If we have a certain model family, generally the algorithm there are some algorithm that is more suitable than the others, and the choices are generally limited. So when we consider that, we can consider the algorithm as something that is fixed, and the 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 choice of question now is we need to fix a range of a range from which the hypothesis can come from. That is the capital H, the hypothesis space. Given a hypothesis space, among all the hypotheses, we can have an optimal expected loss. That is the bias of this hypothesis space. Okay. So intuitively, if the bias is with respect to the hypothesis set, one would think that if we use a large enough hypothesis set, and the set can include many hypotheses, when the hypothesis when you have ample choices, the chances that you will be able to choose one that make the prediction well. So that is a good intuition, but the other side of the coin is variance. When considering variance, we come back to our sense, go back to the real world, and consider the fact that actually nobody's going to have an infinite training sample set, so that he or she is able to find the optimal H bar in the entire hypothesis set. So one have to be happy with whatever hypothesis one can find using the current dataset, and when we do not apply any random algorithm tricks, the dataset is unique. One has only one copy of the dataset, and that training dataset has been drawn from the data distribution, and one has one sample of the dataset. Considering this individual sample, it is natural to consider if you have a large hypothesis set, you have a greater chance that because you have some peculiar sample, so that the learned model, that particular H star something, H star I, arrives at, here we must have H star 1, because we have only one training sample, training dataset. This H star 1 could have a long way to go to the optimal optimal H bar. So on average, the distance of a learned hypothesis to the optimal hypothesis one would have if one were given infinite training samples. This distance, when we take expectation of, again, expectation over all possible training data sets, this average, we call it variance. The formal derivation is as shown in this slide. Note one thing, that in this derivation, we fix a pair of data sample, that is x and y. And for the varying quantities, not actually quantities, the varying factors in the derivation we are considering is the hypothesis and the training data set. Actually, we consider if we randomly draw a training data set from the data population and using the learning algorithm to arrive some learned hypothesis or predictor, how the predictor behave on this pair of particular x and y. So keep in mind that x and y, as opposed to their common rule in equations we usually encounter, they are fixed values here. They represent a particular pair of data sample, and the variables we are considering, the varying factors, are the hypotheses or predictors. So the equation represents that the expected error of a learned hypothesis is prediction on x, and its squared error to the target value y can be decomposed into two parts. One part is the bias, which is if we could find the optimal hypothesis h bar or the optimal predictor h bar, and use this h bar to make a prediction on that x. Consider this optimal prediction, the difference between this optimal prediction and the target value y, call that bias. And the other part is an expectation over all possible training data set. That is a distribution over all hypotheses that could be learned. They are equivalent concepts, okay? And after taking this expectation of the prediction of prediction at x by the hypothesis, we learn from some individual training data sets. This prediction consider is the difference from the prediction that has been made by the optimal hypothesis h bar. So on average, we call this part variance. The full derivation is listed here. Well, it looks a little bit scary, but let us have a look at the essential steps. The first essential step is the manipulation of the term 2 times hx times h bar x. If we add 1 this term and minus 1 this term, where the equation is essentially balanced by introducing this workaround, we will be able to make a squared difference, and using this squared difference, we can derive the term of variance. The second important mathematical manipulation is that we can have the h bar x moved out of the expectation, because although h bar is itself the result of expectation over all training data samples, but having taken the expectation, h bar itself is a deterministic variable. It's a deterministic quantity. It does not vary with the particular training dataset. The expectation has been taken over in these equations. And thirdly, and interestingly, having moved the h bar x out of the expectation, in the expectation we remain that taking the expectation over all training data samples, consider the arrived learned hypothesis, its prediction on x. And this expectation, having taken it, we will arrive exactly h bar x. Therefore, we get the term of h bar x to the square. Let's consider a particular example of using some model families and to fit the model to a particular toy data set, and consider its bias and variance. We consider a particularly parsimonious situation of observation. The dataset itself is simple. The x part is a real number, and the y part is also a real number. So combine the observation and the target value, the dataset makes some two-dimensional distribution. The dataset is from the two-dimensional distribution. But at each time, we assume that we can only observe 2 points from this distribution. So given this setting, a natural idea is that because we have only 2 points each time, so probably we cannot build anything more complex than a straight line on the 2D plane. So let us consider a model of a straight line fitting these two data samples. Here is one example of fitting a line of the two training data sample, and here is another example of fitting another line of two training samples. We can see these two lines could be quite distinctive from each other. And how about we repeat this experiment multiple times? Look, we can afford this because we know this unknown data distribution. Look, now in doing this experiment, we take the God's view of the situation. In practice, the unknown data distribution remains unknown always. But in this experiment, we consider that we know the unknown distribution, and we can actually draw the two simple data sets multiple times from this distribution. And let's see how the model fitting goes. So here are the models. Let us concentrate the smaller range on the y-axis and draw the data distribution that we have already known. In this case, they look like this. Now it is clear that the actual data distribution is an upgoing curve. So probably a straight line can somehow model it, but not very good. But whatever, let us draw our optimal h bar and the variance we computed from multiple experiments. It is shown that averagely the bias is the distance between the green, the dark blue straight line and the red curve. That is the difference between the optimal hypothesis prediction at each x from the target value and from the true target value, because the true target value is of course according to the data distribution. And on the other hand, the blue shaded area represents the variance of the model. It can be seen that when the x goes to the border area of the curve, the variance can go up significantly. So one needs to expect large prediction error when the x goes to somewhere that is a little bit generalized out of the middle land. Then how about we deliberately limit our capability of modeling the data? So instead of using try to fit a straight line on the two simple of the training dataset, let us consider a constant value model. This model is really dumb. It just predicts the constant value for whatever input of the x. So to train this model, well, is straightforward. Given two values we take is their mean. That's it. That is the constant value a model should predict for all the input x. How such a model would perform on the dataset? Let's have a look at if we train multiple such constant models on the dataset. Well, that is the case. And when we draw the bias versus variance plot on the dataset and using this model family, it is like this. Of course, the dark blue straight flat line in the middle will be the optimal H bar, and it is pretty much the average target value on the entire dataset. But look, the variance on this type of the model is much smaller than the variance than the straight line model. So, to summarize, this example, although despite its simplicity and minimalist style, this example shows us that if we use a model which complexity is overstretching the information that could convey in the training dataset, we risk at having very large variance and ended with bad predictions, although we might be satisfied with the training errors because a complex model tends to have fit whatever kind of data better. But the problem is, will be the training dataset typical enough to represent the unknown data distribution? So when one uses a more complex model, one must always consider such balance between the model complexity using a large hypothesis set and risk at having a very large variance at the predictions. The stochastic models or the random algorithms we introduced earlier in this class is a systematical way of striking a good balance between the model complexity and reduce the variance. Of course, when the training data allows us, it is would be silly if we use that dumb constant model, because when it allows you, when you can afford, you should build more model complexity to reduce the bias. Otherwise, even you can reach the optimally trained, the best hypothesis in your hypothesis set, but the hypothesis could be useless, although it is optimal in among all your choices. So in these stochastic algorithms, they gradually build model complexity one step by another. In each step, the weak classifiers, we call them weak for a reason, because we would like them to be weak. They need to be weak, but it's better to be independent with each other. In this way, in each time we bring in a weak classifier in the random algorithm, we would reduce the model bias a little bit and increase the model complexity a little bit, with the hope that the increased complexity will not necessarily increase the variance very significantly. So that is the motivating design principle of many of the stochastic algorithms.